Welcome, everybody, to this latest edition of Stars, Cells, and God. This is the podcast where we explore some of the latest discoveries in science and discuss how these discoveries provide evidence for the Christian faith. My name is Rana. I'm a biochemist and a Christian apologist, and I also work for an organization called Reasons to Believe, which sponsors this podcast. If you want to know more about Reasons to Believe, please visit our website, www.reasons.org. And also you can follow us on social media, RTB_official. And then last but not least, if you're watching this podcast, please go to our YouTube channel, Reasons to Believe, and subscribe, and then also set a reminder so that you get notified when the next issue of Stars, Cells, and God drops. I'm joined today by Dr. Hugh Ross, who's an astrophysicist and the founder and president of Reasons to Believe. And Hugh and I are going to be talking about two discoveries today, one dealing with molybdenum and one dealing with silicon. So, Hugh.
Well, I purposely picked this discovery because I think it's something that we can both weigh in on. It's got astrophysical significance. It's also got biochemical significance. And it's a paper published in the Astrophysical Journal. This is the paper right here, one of the more recent issues. And it's basically trying to solve the problem, where did Earth get all of its molybdenum? And compared to the rest of the universe, Earth has about 5 times as much molybdenum as what we would expect. And so the search has been on for a number of decades. Where did all this molybdenum come from? And I think what's significant, Fuzz, for biochemistry, molybdenum is one of the 22 vital poisons.
Yeah.
These are elements in the periodic table where if you got too much in your body, it's bad for you or it can kill you. And the too little can also kill you. And the molybdenum is on the list. So you want to have just the right amount of molybdenum in your body. Too little is really bad for your health, and too much is bad for your health. It's something I discussed in this book that I wrote, Improbable Planet, and you can actually see a chart in there of all the different vital poisons. But molybdenum is one that's been a mystery to astronomers. Where did all this molybdenum come from? And this paper basically solves the problem, saying that most of the molybdenum that we see here on planet Earth must have come from a hypernova. And you say, well, what on earth is a hypernova? Well, it's a supernova that's on steroids. So, and I got a slide here showing you what a typical supernova looks like.
Right.
This is one that exploded in 1994. And you can see that that star at the bottom left is the supernova. And for a period of about 2 or 3 months, it shines with the brightness of an entire galaxy.
Right.
Now, a hypernova is a star that explodes as a supernova that's more than 30 times the mass of the sun. Those are the most massive stars in the present universe. And that's what, and when they explode, it's called a core collapse supernova, where there's this catastrophic collapse much more rapidly than you see in typical supernovae. And you wind up with a supernova where the kinetics is at least 10 times greater than what you get in a typical supernova. And it's that extreme kinetics, the very fast movement of material out from the star that produces the molybdenum. And the next slide shows you one of the few hypernova that astronomers have actually been able to photograph. It's at quite a distance. But here you can see that the hypernova is many times brighter than the entire galaxy in which it was, in which it exists. It's about 100 times brighter than a typical supernova. And so the whole paper is basically analyzing the kinetics that enables as much molybdenum to form as it does. But
So the molybdenum is actually then forming in the processes that are the nuclear processes that are resulting from that very rapid expulsion of material after the core collapse. Is that right?
Right. Well, when you look at elements in the periodic table, some of them are S process elements, which means they're formed by slow moving neutrons. You got the R process, rapid moving neutrons. This is what's called the gamma process. So there's a few elements in addition to molybdenum that form by this process, but they need the kinetics of a hypernova. Now, there are other pathways to make molybdenum, but they don't make much. To get a lot of molybdenum, you need to have your planet forming adjacent to a hypernova. So what this paper is implying is that our solar system, when it was just forming, must have been exposed to a relatively nearby hypernova, which would have been bad for life.
Yeah.
But if you're talking, long before life exists, this would be in the very early history of the solar system. But the fine tuning's involved because if you got the solar system too close to the hypernova will destroy it.
Right.
If it's too far away, it won't get enough molybdenum to sustain future life. And you say, well, what on earth does molybdenum have for life? There's not a lot of molybdenum in your body. Just it's a trace element. But for example, we know it's much more abundant in bacteria. There's over 50 enzymes in bacteria that require molybdenum.
Yeah.
With mammals, we know there's at least 4. And some of the more recent discoveries is they've recognized that molybdenum is especially abundant in your tooth enamel. And you're the biochemist. I was kind of reading up on it, trying to figure how does molybdenum enhance the hardness and the longevity of tooth enamel. But evidently it plays a crucial role because they've noticed that people who live in a region has very little molybdenum in their soil, and hence they're eating vegetables that are molybdenum deficient, that they have tooth enamel problems.
Oh, interesting.
Yeah.
Unknown to me, but yeah,
Well,
interesting.
the biggest health risk is esophageal cancer. And so there's one region in the world where the soil is relatively deficient in molybdenum, and it's a region that extends from Iran all the way through to North China. And what they've noticed there is that the population has a much higher incidence of esophageal cancer than America. Now, we're in California. Our soil is relatively molybdenum rich. So if you're eating vegetables that have been growing here in California, you got plenty of molybdenum in your diet, and your risk of esophageal cancer is lower than it is in parts of the U.S. that don't have as much molybdenum in their soil. And definitely, it's more than a factor of 10 better than people living that strip from Iran to North China. And this is just kind of an emerging research of people that are saying maybe there's health issues we've been ignoring concerning molybdenum. One that surprised me was baby formula, that when they make baby formula, they need to enrich it with molybdenum. And if they don't enrich it with molybdenum, you see molybdenum deficiency issues in the child. And typically it's been ignored because it's not as significant for an infant as it is an adult. With an adult, if you've got inadequate molybdenum in your body, you're not going to be able to digest foods that are rich in sulfur.
Yeah.
And a lot of our foods are sulfur rich.
Yeah.
And so this leads to dietary problems.
And some of that could very well be the fact that there are microorganisms in our intestinal tract that are making use of molybdenum, in enzymes that are part of their metabolism. And so it could be.
That could be, Fuzz, because I was wondering, given that bacteria have got 50 plus enzymes that are molybdenum dependent, maybe there's something about our gut microbiome. I haven't found any literature on this, but if you're an expert on this, I'd love to hear it.
Well, I'm not an expert on it. I'm just, at this point, just merely speculating.
Right.
But, and so people watching this, please take this for what it's worth, just simply armchair speculation. But we do know that the microbiome actually is critical for our health. And part of what our microbiome is doing in our gut is helping us to actually break down and digest food stuff. And I think, if I'm not mistaken, there have been some studies where in mice where they've stripped the microbiome from the mouse and noted that they were, unable to grow as well as mice that had the functioning microbiome. And some of it is they're not simply getting the nutrients, even though they both were consuming the same quantities and same types of food. So I suspect that it's probably not only, the need for molybdenum in our bodies, but also probably the microbiome is making use of molybdenum.
Yeah, especially given that there's many more enzymes in bacteria that are molybdenum dependent than there are in mammals. And I did a little bit of reading too on what happens if you got too much molybdenum. And that's quite rare. Much more common is molybdenum deficiency.
Yeah.
But there are rare incidences where you have people getting too much molybdenum. And I got a couple of slides for that too. The next slide actually shows you some pure molybdenum. The one on the left is 99.9% pure molybdenum. That little cube over there, 99.999% pure molybdenum. So it's a shiny, hard metal. But typically it appears as molybdenite. And so the next slide actually shows you where we mine most of our molybdenum. This is a quartz crystal, and you've got molybdenite, and that's like 50% molybdenum. And so this is where most of the industrial, because molybdenum also serves a role in industrial applications. It shows up in a lot of specialized steels and different alloys. So it's got a significant industrial application. And the richest source is molybdenite, but it also shows up in all kinds of molybdenum compounds that you see in soils at a very low level, which is what we consume in our diet. But they have noticed that people who are in an area that's rich in molybdenite, that they can wind up getting too much molybdenum, and the toxicity basically affects your organs, the kidneys, the liver, and the lungs in particular. So, but it's extremely rare because it's hard to get too much molybdenum in your diet. If you happen to be in an area like this, that could happen. Much more common is where you don't have enough molybdenum. But we live on a planet that seems to have the just right abundance of molybdenum in its crust. And so we have very few incidences of molybdenum poisoning and very few incidences where people don't have, the vast majority of the population has precisely the amount of molybdenum that they need in their bodies. So just an argument for design.
Yeah, it's fascinating. Well, and then to even extend it, the argument, and I've heard you make this point before, it's not just simply that, that we have the enrichment of elements in the Earth's crust that make life possible, but it's also, it makes advanced civilization possible. So it seems to me like with molybdenum, you could actually make both types of fine-tuning arguments, not only for life, but for...
the industrial applications are important. We wouldn't have the advanced civilization we have if we didn't have the amount of molybdenum. So the fact that we live on a molybdenum-rich planet really helps explain our high-technology civilization.
I've not done any of this work, but as I'm here listening to you talking, it seems to me that this is an opportunity to develop kind of a prediction, a scientific prediction that we could test. And it would be interesting to, I don't know much about molybdenum and its role in biochemical systems, but it'd be interesting to find out what is special about that metal when it's incorporated into enzymes as a cofactor that makes it so useful. And I would predict that you're going to find that molybdenum has these just right properties that you can't replace, that there's not alternatives to the molybdenum enzymes. And so that
you're exactly right. It's the only element in the periodic table that binds with oxygen in such a way as to form a particular geometric pattern that allows certain proteins to function. So people go in the Wikipedia article on molybdenum, they'll actually see this incredibly complex three-dimensional structure that's crucial for these cofactor enzymes.
So, I mean, that would extend the argument, right? That where you would say that not only is, so in other words, it's not simply that, life is adapting to what's available, right? And creating molybdenum enzymes because that molybdenum is available, but rather if molybdenum wasn't available, there's a certain range of biochemical functionality that wouldn't exist that makes life possible. So,
you'd be missing certain proteins, and without those proteins, no life is possible anytime, anywhere in the universe. You got to have molybdenum. Well,
and it may seem like a subtle point, but I think it's really important because you hear skeptics oftentimes say, "Well, it's just like that the water that finds itself in a puddle," saying, "Isn't it amazing how ideally shaped the puddle is, for me, right?" And so the idea here, to take that objection and then talk about it in terms of, evolutionary theory, you would say, well, life again is just evolving based on what's available in the environment. But I think really what is behind the anthropic principle is the fact that we live in a universe where concave surfaces are even possible.
Right.
Right. That if things were even slightly different, we'd be in a universe where only flat surfaces or convex surfaces are possible, not concave surfaces. And I think that's really, the point here, right, is that it's a necessary component for life, and life simply wouldn't be possible without it.
Yeah, and that's true of virtually every element in the periodic table. I mean, the reason I made the table in Improbable Planet is like when you look at the periodic table, virtually every element there is anomalous with respect to the Earth.
Mm-hmm.
The Earth is either super abundant in the element or super underabundant. And that underabundance or overabundance is exactly what life needs.
Yeah.
And so we're not going to, that's one argument why we shouldn't expect life to be on all the planets in the universe, is that those planets aren't going to have the right abundance ratios of the periodic table elements.
Yeah.
Okay, let's talk about silicon.
Okay, yeah. Well, I'll give our viewers a quick mental break here and talk a little bit about some trivia before we get into the discovery. And I'm actually going to ask you a question. It's a very controversial question, Hugh. So be careful how you answer this question.
It's got anything to do with music. I'm out of the...
Well, it has to do with science fiction.
Okay.
But the question I want to ask is do you prefer Star Trek or Star Wars? And be careful how you answer, because for some people, that's a question of orthodoxy, right? In pop culture, if you answer that question the wrong way, you're a heretic.
Well, I'm probably a heretic no matter what I say, because I really don't watch much science fiction.
Yeah.
I have a problem with both Star Trek and Star Wars in that when you watch it, they're just violating the laws of physics way too many times per minute. And my toleration level, I can handle if they violate the laws of physics maybe once a minute, but when it gets up to 6 or 8 times a minute, I have problems watching it.
Yeah. Well, I'm not going to answer that question either. But the reason why I bring that up is because I'm going to be talking about the prospects of life being based on silicon. So there's going to be some interesting connections between your discovery and what I'm going to talk about. But invariably, when you talk about the prospects of silicon-based life, people that are writing the lead for the article or coming up the lead to use in the podcast bring up this particular creature,
okay,
which is called a Horta. And this creature was a creature that featured in one of the last episodes of season 1 of Star Trek, the original series. And the episode was called Devil in the Dark. And it was about...
Fuzz, it looks like a bunch of, ketchup poured over...
Yeah, well,
over burnt hamburger.
We'll see in a minute why actually this was the way they depicted the Horta. But so the idea is that the miners on Janus 4 were dying. They were being killed by some kind of mysterious creature. And so when the away team went down on the planet, they discovered that it was a silicon-based life form. And Spock does a mind meld and discovers that it's just a mother trying to protect her young. So It's a very endearing episode. But the guy who wrote that episode, Gene L. Kuhn, this is the trivia part, probably got his inspiration for this episode from a short story written by Isaac Asimov.
Yes.
Called The Talking Stone.
Mm-hmm.
And Asimov wrote about a creature called the Silicone. So if you think about coney, like a rabbit-like creature. Yeah. So clever play on words. But here's how he describes it, just for fun. Its skin was of oil, was an oily, smooth grayness. Its motions were slow, as became a creature who burrowed in stone, and was more than half stone itself. There was no writhing of muscles beneath the skin. Instead, it moved in slabs as thin layers of stone slid greasily over one another. It had a general ovoid shape, rounded above, flattened below, with 2 sets of appendages. Below were the legs set radially. They totaled 6 and ended in sharp, flinty edges, reinforced by metal deposits. Those edges could cut through rock, breaking it into edible portions. On the creature's flat undersurface, hidden from view, unless the silicone were overturned, was one opening into its interior. Shredded rocks entered that interior within limestone. Hydrated silicates reacted to form the silicones out of which the creature's tissues were built.
So this thing ate stone.
That's right. That's right. But it's these kind of ideas that are found in science fiction that I think really convince a lot of people, that both in the scientific community and lay people alike, that there's really nothing necessarily special about life on Earth, that it's possible that maybe there could be life unlike we know it.
So carbon's not the only game in town.
Right.
It doesn't have to be life as we know it.
Yes.
It could be an alternate form of life.
Right. And so what I want to talk about today is, can life be based on silicon? And, this question is significant because from a pure scientific standpoint, it factors into how we understand what life actually is. It factors into the origin of life question and into astrobiology and the search for life in other locations in our solar system and maybe even beyond. But from an apologetic standpoint, when you talk about examples of fine tuning, right, in our universe, the underlying assumption is that it's carbon-based life that finds itself in an aqueous medium. And so the rejoinder oftentimes is, well, you're just assuming life as we know it. What if it's life as we don't know it? Then maybe this fine tuning just simply evaporates. And so that's what I want to take on today. And this is the paper I want to talk about. It's written by some scientists from MIT. And one of the things that's interesting in the introduction of this paper is they point out that when it comes to the prospects of silicon-based life, which actually was proposed by an astronomer in the late 1800s, that idea has been around.
It's been around a long time.
For a long time.
So,
what they point out is that people either uncritically accept that possibility or they reject it outright. And they point out very few people actually have rolled up their sleeves and done any kind of work to actually address that question. And so what they've done in this paper, it's a review article, but they literally have gone through the literature on silicon chemistry and silicon biochemistry and really have done a critical assessment of what did the experimental results actually tell us. So it really is a very fine piece of work. And one of the sections of the paper, which in and of itself is worth the price of admission, is their discussion on the chemical requirements for life. They present a really detailed discussion of what does life actually require, from a chemical standpoint. And bottom line is that, life requires chemical complexity.
Right. And stability.
Right. If you're going to have living systems, even the simplest system is incredibly complex. You have to have a corresponding chemical complexity. Another way to say it is you have to have chemical diversity. And that diversity, this is something that really is well done in the paper. They discuss the fact that diversity actually takes on two faces. One is structural diversity. You have to have life being based on an atom that is capable of producing a wide range of different types of structural molecules. So that would be the scaffolding. There has to be a diversity of molecular scaffolding for life to be possible. And that scaffolding has to have a stable backbone. It has to be stable.
It's got to be stable.
Right. But you also have to have a wide range of functional diversity as well. And they point out that there is a balance with both the backbone as well as the functionality between reactivity and stability. Because if you have too much stability, then nothing is going to happen. If it's too reactive, then the system is in so much flux that you don't have the stability you need for life. So there's, you have to have an element that gives you a pretty expansive collection of chemical properties, both structurally and functionally, in order to have life. And carbon is perfect towards that end. Carbon has an incredibly rich chemistry. And this has been recognized for well over a century, that not only does it have a very rich chemistry, but it seems to be a highly unusual chemical element towards that end. There's very few chemical elements that have the type of rich diversity of chemistry that you see in carbon. Just as a point of comparison, if you're a chemist, you can specialize in organic chemistry, which is the chemistry of carbon compounds, or you can be an inorganic chemist, which is a chemist that specializes in the chemistry of everything else on the periodic table. And that's because we know right now of at least 10 million different organic compounds that are built from carbon. And that doesn't include the number of inorganic compounds. So it's an incredibly a molecule with incredibly rich chemistry.
Now, are you going to share with us the comparison between what's possible with carbon being 10 million and what's possible with silicon?
Yes, I sure am.
Great.
But carbon is a really great illustration of what you need, again, for life to be possible, because carbon can forms 4 chemical bonds. Its valence in chemical terms is 4, but that valence can be 4 single bonds, 2 single bonds and a double bond, a single bond and a triple bond. Now, this is important because the double bond and the triple bond impart reactivity actually to the backbone, but the different bond formations have different molecular geometries. 4 single bonds are tetrahedral. A double bond and 2 single bonds form what's called a trigonal planar structure, and then a triple bond and a single bond form a linear structure. Mm-hmm. And so this gives you, with these different kinds of bonding, the ability to vary the geometric arrangement of atoms in the backbone,
which is crucial for proteins.
Right, and DNA and even fatty acids. And so that's a really critical property. It forms the carbon-carbon and carbon-hydrogen bonds are stable, and that allows the formation of linear chains, branch chains, rings that are fused with other rings, and even it allows for a special type of chemical bonding called aromaticity, which is really critical not only in terms of structure, but also in terms of functional capability.
And that plays a crucial role in how planets form. Without that sticky carbon, you're not going to get planets forming.
Yeah, interesting how it all connects in kind of an eerie way. Carbon forms stable bonds with heteroatoms, anything other than carbon and hydrogen, oxygen, nitrogen, sulfur. And with oxygen, it can form a wide range of different types of functional groups. And so you have the chemical diversity, both structurally and functionally. And again, carbon straddles that balance between stability and reactivity that you need for living systems. Now, all of this is assuming we're dealing with an aqueous system.
Yes.
Right. And in fact, water's interaction, or the interaction between water and carbon compounds, is also critical, because many carbon compounds are actually water soluble, which is important in a living system. But some carbon compounds are water insoluble, which creates a phenomena called the hydrophobic effect, which I'm not going to get into, but if it's not for that effect, life isn't possible.
You're not going to have cells.
You're not, and a whole bunch of other things you're not going to have.
Right.
Well, proteins fold, DNA adopts a double helix, membranes assemble because of the hydrophobic effect. So the point here is that it's not just simply that carbon has the just right set of properties, but that its interaction with water is just right as well. And of course, water has a whole litany of just right properties that we won't get into, just for the sake of time. So when we talk about this question, can life be based on silicon? What we really need to do is look and see, does silicon satisfy these properties? And now, silicon is about the best possible choice for life as we don't know it. Because if you look at this periodic table, you can see let's see, this would be group 1, 2, 3. Group 4 is where carbon is located. And any element in the same column will have the same, or very similar, not the same, similar chemical properties. So because silicon is right below carbon, if there's any element that has any possibility of serving as the basis for life. Other than carbon, it would be silicon.
Mm-hmm.
Nothing else really is even close. And silicon actually has a lot of similarities with carbon. They both are 4A elements. They both form 4 covalent bonds. Silicon can form silicon-silicon and silicon-hydrogen bonds, and it can form bonds with heteroatoms. So on the surface, silicon does seem to have the chemical diversity that at least puts it in as a possible prospect. And so when you have Isaac Asimov writing his science fiction story about the Silicone, what he's doing is really good science fiction, because he's taking ideas that were in play, that were legitimate scientific ideas, and then just extrapolating them just enough to make them impossible, but it creates a believability, but yet allows him the impossibility space to explore different ideas creatively. So that would, to me, is the good example of science fiction where there's only one or two things that are departing from
No, I
what
got
we
a
know.
question for you. Assuming you've read this Isaac Asimov piece.
I have, yeah.
Okay. How did he deal with the solubility issue? I mean, what kind of fluid does this?
Well, he doesn't deal with that
Doesn't
issue.
deal with that, but you're going to deal with it, right?
I hope so. I might deal with it, yeah. But what's interesting is that even though there's this similarity, the authors of this piece, this is just a very powerful quote that I think is worth reading. They say silicon and carbon are false twins. Their similarities are superficial and insufficient to mitigate their crucial differences. Chemistry that is stable and normal for carbon is unstable and exotic for silicon. And similarly, chemistry that is unstable and impossible for carbon is stable and routine for silicon. Silicon's distinct chemical characteristics and reactivity make it a challenging choice for life. Silicon-based life that uses silicon exclusively as a scaffold element is often portrayed in science fiction. However, silicon-based life that uses silicon exclusively as a scaffold element is almost certainly impossible, right? So that's kind of the bottom line. And what I want to do real quickly is just, again, I apologize for the slides, but there's just a lot of technical detail here that I think.
Hey, I love these slides.
Yeah, but my point in showing this, going into this detail, is that for some people that have a background in chemistry, this will make sense.
Right.
Others it won't. But what I want to do is just simply show that this conclusion is not based on just simply armchair speculation, that they've done a detailed characterization of silicon chemistry. Now, for example, the silicon-silicon and silicon-hydrogen bonds are actually weaker than the carbon-carbon-carbon-hydrogen bonds. And this is because silicon is below carbon in the periodic table, which means its atomic radii is larger, which means the bond lengths are longer, and the longer bond lengths weaken the chemical bond. So the backbone is intrinsically much more reactive for silicon scaffolding than it is for carbon scaffolding.
So that would pose a real problem for silicon DNA.
Yes, yeah. And again, this is all assuming an aqueous environment. Silicon has low-lying 3D orbitals. Now, this is, for people that are chemists, this again makes sense. Now, what ends up happening is, because of that, silicon can actually form compounds with a valence of 5 and 6, which on the surface would add to its chemical diversity. But what ends up happening is, again, it makes silicon-silicon bonds more reactive compared to carbon-carbon. Carbon-carbon doesn't have access to 3D orbitals, the carbon atom, to allow for these higher order valences. So that again undermines the stability of the silicon scaffolding. Silicon can't form double and triple bonds. And then silicon reacts extremely aggressively with oxygen. Carbon doesn't do that. Now, this is problematic because, number one, it means that most silicon compounds are going to, in the presence of oxygen, convert into silicon dioxide.
Right.
And you have to think of silicon dioxide as kind of the analog to carbon dioxide. Now,
except it's solid.
It's solid. Well, yes, this is a huge point, right? It's solid, whereas CO2 is a gas. Now, and what happens is when you have silicon and carbon forming compounds, carbon naturally will form and prefers to form carbon-carbon bonds. Silicon prefers to form silicon-oxygen bonds. That's the preferred bonding. And again, this is really significant because it means that these silicon compounds aren't stable, but it also means that if you had a hypothetical organism that was using silicon, the way you would extract energy is to take silicon in a reduced state and oxidize it to silicon dioxide. This is what happens with carbon. You have carbon in a reduced state, you oxidize it, and generate CO2 and water as the breakdown products, and you're extracting energy. It's like a combustion reaction. You take a piece of wood and burn it, you get CO2 and water. The cells, or your biochemistry is, in a sense, burning, carbon compounds, but it's under a highly controlled set of chemical reactions.
And it can get rid of the carbon dioxide.
Yes.
You're not going to be able to get rid of the silicon dioxide. That for people who don't realize, that's sand.
Yeah.
So,
well, that's right. Well, now this is significant because CO2 is not only a gas, but it's soluble in air and it's soluble in water, which means that when a cell breaks down stuff and produces CO2, the CO2 can diffuse away from the cell and into the atmosphere. If you're a silicon-based life, you're going to wind up with sand cluttering up the cell.
Yes.
And so that in and of itself, that one fact in and of itself probably makes silicon-based life impossible. But that solubility property also makes photosynthesis possible because organisms can take CO2 from the atmosphere, incorporate it into the cytoplasm as dissolved CO2, which then is available to react to form sugars in the dark reactions of photosynthesis, right? And so this is really significant, and in and of itself suggests design that if it wasn't for these unusual properties of CO2, life simply wouldn't be possible. CO2 gets a bad reputation because of climate change, but the fact of the matter is CO2 has these incredibly just right set of properties.
And it's very abundant.
Yes. So anyway, so the point, then one other point here, silicon is more electropositive than carbon, which means the bonds with heteroatoms are polarized and more reactive. So
now, a couple of slides ago, I saw that you said that with silicon, you can't get triple silicon bonds.
Yes.
Is that accurate?
Yes.
Okay. Wouldn't that rule out light by itself?
Well, it's a hit to the use of silicon as molecular scaffolding, as well as the functionality. Right. So anyway, so what I want to kind of talk about now in terms of kind of the
I love this slide.
Yeah. In terms of the apologetic significance, because obviously what we've established here is that that it's the likelihood of life being unlike we know it is really, really remote. That, in other words, the fine-tuning arguments that you make are robust arguments because, again, they are based on the assumption that life is carbon-based in an aqueous environment. But what this paper is showing is that is not only a good assumption, it probably is the only likelihood that you really have for living systems. So it means that these fine-tuning arguments actually stand. But what to me is really eerie about all of this is that what it's showing us is that carbon seems to be a unique element compared to all other elements in the periodic table in that it has the just right chemistry needed for life, that the closest analog to carbon, silicon, fails. And so carbon has these just right properties. It's unique. And of course, its properties are fundamentally specified by the laws of nature. So it's almost as if, whoever brought the universe into existence did it in such a way with the idea that an element like carbon would exist so that life is possible. So it's like a divine conspiracy at play.
Not only exists, but exists at the right abundance levels relative to the just right abundance levels of oxygen, nitrogen, phosphorus. We can go on.
Yeah. Well, so, and I
oh, here we go.
Yeah. So I've got a cosmic.
Nice.
I figured you would love this slide.
Oh yeah, definitely.
But what's amazing is that when you look at living systems, they are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Those are the dominant elements in living systems, the CHNOPS or whatever the acronym is. And of course, there's other, as you're pointing out, there's other atoms that are absolutely vital for life, but those are the elements that are really used to build the biomolecules.
And Fuzz, this is logarithmic. So when you see carbon, nitrogen, and oxygen there, that's a factor 10 above everything else that follows it.
I didn't actually appreciate that point. That's actually even makes it even more compelling, right? But what's remarkable is that the distribution of chemical elements corresponds to the chemical elements that you actually need for life to be possible. So it's not just simply that carbon has the just right properties, it's unique, it's fundamentally dictated by the laws of nature, but it's in the right abundance, in the right distribution.
And look where iron is. Iron is crucial for biochemistry, and
yes.
Look how high the abundance of iron is.
Yeah, iron plays an absolutely central role in so many different biochemical processes. What's also even adding to the series of anthropic coincidences is the way in which carbon forms. It's the triple alpha process. And this was what Fred Hoyle discovered, where you have to have this just right resonance between the energy levels of the beryllium nuclei, carbon nuclei. Oxygen has to have a just right off resonance. Otherwise all the carbon that forms would wind up being converted into oxygen. So you have this collection of nuclear energy levels that are just right. As I understand it, the decay rate of the beryllium nuclei has to be just right relative to the frequency of collisions. And then there's other...
I've got a whole talk on that, Fuzz, about what's happening with that triple alpha process.
Well, I would actually love to hear it. But there's other things that have to be fine-tuned that I don't fully appreciate as a biochemist, that you probably will, but the strong force has to be fine-tuned, the Coulomb forces, the Higgs vacuum expectation value and quark masses must be constrained. So the level of fine-tuning goes beyond what Hoyle discovered. It's
not just Hoyle. It was Burbage and Burbage, husband-wife team, Willie Fowler and Fred Hoyle. And Willie Fowler was the one who really did the work on all the physics and the nucleophysics that makes this possible. He actually taught a course in this at Caltech. And our own Dave Rogstad took that course from Willie Fowler.
Fun.
So if you really want to understand all this, go talk to Dave. He can give it to you in all the gory detail that Willie Fowler taught it. But it's actually the most cited paper in physics.
Wow.
Yeah.
Wow. But to me, it's remarkable when you start looking at the anthropic coincidences just centering around carbon. And again, in as an offshoot, carbon dioxide and its properties are also should be considered when we start thinking about carbon. That again, the distribution of carbon in the universe is just right.
Well, if it's not for really extraordinary fine tuning, you'd either have a universe with carbon and no oxygen, or oxygen and no carbon.
Yeah.
To get both relatively equal, be able to have carbon dioxide and water existing in the universe is an outright miracle.
Yeah. So what's interesting to me is that today, and we didn't even talk about this, we both ended up choosing discoveries about chemical elements that highlight really the remarkable fine tuning that we see in aspects of the universe that I think at first glance most people wouldn't even think actually have to be exquisitely fine tuned for life to be possible. And so it just looks like there is a divine conspiracy, that everything is just right.
Well, Fuzz, you showed that periodic table. We may be living on the only planet in the universe where all those elements show up.
Yeah.
And you need them all.
And just think if we weren't in another place in the universe, there would be no chemistry, no chemistry courses, no chemistry degrees.
In the lecture I teach about how we have all this carbon and oxygen, nitrogen, just the right ratios because of fine tuning, says if it wasn't for that extraordinary fine tuning, all we would have would be hydrogen and helium, which would make passing a chemistry class really easy.
Assuming you'd have chemists take the class.
You wouldn't have chemists, but regardless, your professor wouldn't exist.
Yeah. Well, if people want to dig deeper, I've just had a book published called Fit for a Purpose, where I explore this idea of anthropic coincidences and fine tuning in biochemistry. But you've made your career as a Christian apologist with the fine-tuning argument. So what are some of the books that you've written that people can take a look at if they want to dig deeper?
What I was really impressed by your Fit for a Purpose, you actually had a section in there on the triple alpha process and all the fine tuning that's necessary to get the just right amounts of carbon, oxygen, and nitrogen. So I was impressed that a biochemist was there, and everything was just perfect. It was very well done.
Oh, thank you. That's
so
nice
you did a really good job.
I did my homework.
But where you'll find that in detail is in the Crater and the Cosmos 4th edition, because that's where I go in. And by the way, I was also impressed in Fit for the Purpose. You talked about the fine tuning of the strong and weak nuclear forces, which are crucial to get the just right amounts of carbon, oxygen, and nitrogen.
Yeah, so people can check out your book, Creator in the Cosmos. Why the Universe is the Way That It is right. Dealing with anthropic coincidences. Improbable Planet.
Probable Planet is where I go through the whole periodic table, and by all means fit for a purpose.
Yeah. So anyway, I think we pretty much have done what we were going to do today.
This was fun, Fuzz.
Yeah, it was. Well, for me and you, it was fun. Hopefully our audience thinks the same thing. But anyway, I just want to sign off by reminding people that the more we know and discover about science, the more we have reasons to believe. And please, follow us on social media, RTB_official. Don't forget to subscribe to our YouTube channel, Reasons to Believe. Set a reminder. And then also go to our website, reasons.org. Last but not least, just for fun, I'm curious if you're watching this and you want to take the time in the comment section, tell us whether you think it's Star Wars or Star Trek as the best science fiction series on TV or on the big screen. Okay, and so until next time, God bless each and every one of you. See you around.